Okay, today I want to talk to you about complex circuits. We've done some work with series and parallel circuits, and now we're just going to put those two things together and talk about circuits that have parts that are in series and parts that are in parallel. So let's draw one. If I had a series circuit, that just had two resistors in it, let's say like this, but instead of the second resistor, let's say this second resistor was actually two resistors that were in parallel with each other. So if I replace that section right there with something that looked like this, so that the current that was going to go through that resistor was actually now going to split and go some of it through this one and some of it through this one, and then back together again, and then back to the battery. That circuit might look something like this. Battery, first resistor, and then the two resistors in parallel with each other as the second part. Now, if we put some numbers behind that, let's say this resistor here is 8 ohms. And then both of these two resistors are also 8 ohms. Call that an 8 ohm and that an 8 ohm. What do you think the resistance of this complex circuit that has an 8 ohm resistor here, an 8 ohm resistor here, and an 8 ohm resistor here would be? Well, the way you go about solving it is try to isolate the sections that are either in series or parallel. Like, for instance, these two, as we see, are in parallel. And when you have two 8 ohm resistors in parallel, you can use the formula 1 over R total is equal to 1 over R1 plus 1 over R2, and plug in 1 over 8 plus 1 over 8. Add them together, get 2/8, find the reciprocal of that, and your total resistance is going to be 4. So if this combination actually has a resistance of 4, what I really have is an 8 ohm resistor in series with a 4 ohm resistor. And so the total resistance of the circuit would then be 12. Here's a complex circuit with 3 resistors. I'm going to draw a loop here that goes through the first resistor, and then here's one way to go through the circuit, down through the second resistor and back. If I draw a second path, which goes through R3, you can see that there's really just 2 ways to go through this circuit for the electrons. Both of them have to go through R1, and then the blue one shows that you go through R2 if you go that way, or you can go through R3 and go that way. What this shows is both paths go through R1, which means that R1 is in series with the battery and in series with the rest of the circuit. So R1 is going to have the total current in it, and then R2 and R3, both of these currents are going to add to equal the current through R1 because of the junction rule. All the current that comes through R1 is going to split. Some will go through R2, some will go through R3. If they have the same resistance, then they're going to get an equal amount of current because they're equally viable paths. If, let's say, R3 had a higher resistance, it would get less of the current and R2 would get more of it. But both of those currents, the current through R2 and the current through R3, would still have to add up to equal whatever current came out of the battery and went through R1. And then they would add together, and if I put an ammeter down here someplace, that would also read the total current. If I put an ammeter here, it would read only what went through R2, or here. If I put an ammeter anywhere in this outside part that's just red, it will just read whatever goes through R3. Okay, let's put some numbers in here and keep them simple to begin with. Let's make all of the resistors 2 ohm resistors. And the battery, a 6-volt battery. Okay, now I'm going to put these over into the chart like we did before. This is my first resistor, my second, my third, and then the total goes down at the bottom. So my total voltage is 6. And then my resistors, it doesn't really matter what order I put them in, but I'll put them in order of R1, R2, R3. So I have a 2, a 2, and a 2. R2 is the one down here on the blue loop. R3 is the one on the red loop. And R1 is the one that is on both loops. Figuring out these complex circuits is all about trying to find the sections that are in series or in parallel and combining them together and making what's called an equivalent circuit. What I mean by that is this R2 and R3 right here are in parallel. So if you have two resistors in parallel, you can use the parallel resistance formula. 1 over RT is equal to 1 over R1 plus 1 over R2, and solve for the equivalent resistance or the total resistance of that section, and then replace that section with a resistor that's equal to that. Watch. I'm going to plug in 1 over 2 plus 1 over 2 and get 2 over 2, which the reciprocal of that is also 2 over 2. And so my total resistance for that section is 1 ohm. What that means is I can replace these two resistors with a 1 ohm resistor. So if I want to redraw this circuit, I'd have my battery, I go up through the first resistor, and now all I have is a second resistor that's 1 ohm. My first one is still 2 ohms, and I still have a 6-volt battery. This equivalent resistance circuit is much easier to deal with. It's just a series circuit. I have a 1 ohm resistor and a 2 ohm resistor, so my total is 3 ohms and 6 volts. So that total of 3 ohms, which is the equivalent resistance of my equivalent circuit, I can put in here as the total resistance of the circuit. And you know that for current is V over R. So if I plug in 6 volts over 3 ohms, I'm going to get 2 amps of current. So I have 2 amps of current is my total current. Now, the total current, as we mentioned before, goes through R1. So I can go up here to my R1 and also put in 2 amps there. So I'm going to write in 2 amps up there because I know the total amount of current going out of the battery and through this resistor is 2. Now, when that current gets to this junction, it's going to split. And for this circuit, since they both are 2 ohm resistors, it's going to split evenly. Half of it's going to go this way, that would be 1 amp, and the other half is going to go this way, also 1 amp. So I can plug that in. I'm going to write those in, 1 amp and 1 amp. And then now that I have this full of 2 of the 3 columns here, I can use my V equals IR across. V equals I times R. I know that for this first resistor, it has 2 ohms and 2 amps. So that is going to take 4 volts out of the 6-volt battery. And then the other 2 only have 1 amp times 2 ohms. So they're both going to take 2 volts and 2 volts. Now, you might think we made a mistake here because this is 4 volts, this is 2 volts, this is 2 volts. That adds up to 8. However, what are the rules for parallel circuits? Parallel circuits each get the full voltage of the battery. And so basically, this whole section that's parallel is going to get the full voltage from the point where the current splits to the point where the current comes back together again. So the voltage drop between the two X's I just drew has to be the same, and it has to be added to whatever the voltage drop is up here, which is 4 volts, to equal 6. So on any given loop through this circuit, I have to have 6 volts worth of drop. So 4 volts across here, 2 volts across this one, and I've used up my 6 volts. Or 4 volts across here, 2 volts across this one, and I'm back to the battery. When you do a complex circuit, all of the rules still have to work, but just within their sections, okay? So For this circuit, my voltage drops, as I just said, are going to add up to the total of the battery. Anything in parallel has to have the same voltage. So R2 and R3 both have the same voltage. Okay. Ohm's law has to work across for every single individual resistor. So for this resistor, this is 4 volts. 2 ohms times 2 amps gives me 4 volts. For these two, they both get 2 volts. 2 volts, 2 ohms gives me 1 amp. So Ohm's law works across. Ohm's law works across for the entire totals. 6 volts total, 2 volts total current, 3 ohms total resistance. I'm going to try another one with the same exact setup, but with different numbers. Let me erase. Okay, here's the same circuit, but with different size resistors and a bigger battery. So I have a 24-volt battery, still going through the 4-ohm resistor and splitting, and then going through either a 6-ohm resistor or a 12-ohm resistor. This one is different because it has different numbers for each resistor, but also because the two paths through R2 and R3 are not equal. R2 is easier for current to flow through than R3. And so R2 is going to get more current. In fact, it's going to get twice as much current as R3 because it has a 6-ohm resistance and R3 has a 12-ohm resistance. Let's solve it the same way. First thing we did before was we took R2 and R3 and we found the equivalent resistance. So if you do 1 over 6 plus 1 over 12 to get R total or R equivalent, you add them up and do the inverse of that, you're going to get a resistance of 4. So this combination, this parallel combination of R2 and R3 has an equivalent resistance of 4 ohms. So my total circuit now, I could redraw it down here, is a 24-volt battery connected to a 4-ohm resistance, that's the R1 still, and then another 4-ohm resistance. So I have a series circuit now of 8 ohms. And so that 8-ohm resistance is going to allow 3 amps of current to flow when connected to a 24-volt battery. So I'm going to plug in here 8 ohms and then 3 amps of current. And I'm finding that 3 amps of current just by doing I is equal to V over R for the totals. The total voltage is 24, and the total resistance is the sum of the 4 and the 4, so 8 ohms of resistance. Okay, so now we can go figure out the rest of the Sudoku puzzle here. Or these grids are kind of like Sudoku puzzles because once you figure out something, you can get something else. We know there's 3 amps of current total in this circuit, and that 3 amps has to go through R1. So R1 also has to have 3 amps for current. And since I know that, if I know 3 amps and 4 ohms, I can use Ohm's law, I times R, and find that there's 12 volts used up across R1. That's the voltage drop across R1, 12 of the 24 volts, which means I have 12 volts less to use across R2 and R3. Now, a common mistake I've seen is people would say, okay, that means R2 gets 6 volts and R3 gets 6 volts. But wait a minute, there's only one more voltage drop, remember, from this point to this point. You either are going to go across R2 and use the remaining 12 volts there, or across R3 and use the remaining 12 volts there. So since they're in parallel, they both are going to get 12 volts because you're not going through one then the other. You're going through them and using the 12 volts from one point at the beginning to the other point. So I'm going to write in 12 volts for both of them. And now I've got V and R, so I can do I is equal to V over R just for my individual resistors. So 12 volts and 6 ohms gives me 2 amps. And 12 volts and 12 ohms gives me 1 amp. That follows what we expected, which was that the 12 ohm resistor is going to have half as much current as the 6 ohm resistor. And those two currents are going to add up to my total, which goes through R1 and is the total for the battery of 3 amps.